Okay, now let's have a flying review of what we've just covered here and look at the individual detectors themselves. First, let's look at BF3 tubes. These detectors use boron trifluoride gas, often enriched in boron-10, so that the following reaction creates charged particles in the tube. A neutron interacts with boron-10 to form lithium-7 plus an alpha particle. Lithium-7 is left in the excited state 94% of the time, and 2,310 keV appears as prompt kinetic energy in the products. The excited lithium-7 decays from this excited state by emitting a 480 keV gamma ray sometime later. 6% of the time, the lithium-7 is left in the ground state, and the extra 480 keV appears as extra kinetic energy in the products. The kinetic energy during this 6% decay process is now 2,792 keV. Helium-3 is a naturally occurring but extremely rare form of helium, whose natural abundance is only about 0.000137%. The only practical source of helium-3 is from tritium, is to extract it from tritium after the tritium decays. Helium-3 is still hideously expensive. Helium-3 detectors use the following reaction. Helium-3 plus a neutron goes to a triton plus a proton with 765 keV of kinetic energy in the products. Helium-3 detectors have very similar characteristics to a BF3 tube, but one difference is that the helium-3 itself works as a wonderful counting gas, so you don't have to add another gas to help with the counting characteristics. But they are generally more expensive than BF3 counters. Sometimes extra gases are added to more quickly stop the reaction products, but that's a different story. Fission counters are widely used where you have lots of neutron signal, for example in reactors. They detect neutrons from induced fission of fissile material plated on the inner walls of the chamber. Usually this material is highly enriched U-235. After fission, one of the two fission fragments will travel out from the plated material into the gas. These fission fragments are very energetic. They share 168 MeV between them. However, because they're so highly charged and so large, even with this much energy, their range is very short. The average range in air is a few centimeters, and in U-235 metal, the range is only 7 micrometers, which is equivalent to about 13 milligrams per square centimeter coating thickness. This generally results in a low overall detector efficiency for fission counters. Making the coating thicker doesn't help because the fission products created next to the wall can't escape through the U-235 to get into the gas to generate a signal. Fission chambers are often operated in the ion chamber mode because we've got so much signal from the fission fragments as they traverse the gas, you don't even have to try and collect everything, much less amplify the signal. There is also an alpha background from the decay of the U-235, but who cares? Because you have so much energy from the fission fragments, it's easy to discriminate the fission fragments out of this alpha signal. And as we've seen, gamma rays don't even come to play. Scintillation detectors change the energy from the charged particles that come from the interaction of a neutron to light. And this flash of light is used to detect the neutron. One such device is a lithium-loaded glass. As we've seen, a neutron interacts with the lithium, producing an alpha and a triton. These charged particles deposit energy in the glass, which converts a small fraction of this energy to light. This light is somehow fed to a photomultiplier system to amplify the signal and thus detect the neutron. Depending on what you're trying to detect, these scintillators can come bundled into an array of detectors. This picture is of an array of lithium-loaded glass detectors. We can also use semiconducting materials to build a detector for neutrons. The good news about this type of detector is that you have about 1.5 million whole electron pairs produced per neutron interaction. This signal is so large that it can be detected directly without further amplification. The bad news is that standard semiconductors don't contain enough neutron-absorbing nuclei to give a reasonable neutron efficiency. So what do you think we do? We can add a neutron absorber on the top. The bad news is this absorber can only be a few microns thick, so that the detector efficiency is still relatively low. Our work here is not done, but this concept shows great promise.